To the APSIM, coming to the APSIM review. This has been a really long-running project. It was first started by Justin Fanges when he ported the old classic code in 1996, which just goes to show you that there's a big difference, long haul between just porting code and having something that's ready for release. At least we think this is ready for release. So essentially what I've got here is a pretty short presentation running through what we've done, what's available in the would be available in the release and things like that. And if you want more details, you can head over to the APSIM issue, sorry, the GitHub issue that we used, or you can have a look at the project board that Dean and I worked off. So the final push towards this point has been funded by Ag Research under one of our internal funding projects. And the way Dean and I managed this was to use a GitHub project. And you will see that well, you won't see it, but when we started, we had a whole bunch of cards under the to-do list. Eventually, they moved to in progress and now into done. And actually, I need to update the card about writing a presentation for the review because this is it. And hopefully, we're going to approve the so that we can close the new version of APSIM 1. Right, so key features of the material that we've got ready for release is there's a preamble that describes a bit about the model, validation, which is the statistical part of the testing, lots of sensibility testing. We prepared a tutorial for users, and there's an example simulation. And one of the things that, of course, should be mentioned here is that we've still got Verberg et al. 1996 as the definitive source of information for APSIM, for SWIM, sorry. So in the preamble, which you can see in the generated documentation or in the SWIM simulation, we've got a bit about SWIM, what its special features are, and when you might want to use it rather than soil water, what the major differences are compared to the model as it was described in 1996, an explanation for users about how layering in nodes works, a very short discussion about how to deal with convergence issues and some further development needs that we think would be a good idea, but not essential for first release. In the validation section of the simulation, we've got three different sort of categories. We've got the Hudson simulation that Neil developed initially in Classic, and that's been ported over to the next gen simulation, and it's giving pretty much the same performance as in Classic. From New Zealand, we've got drainage and leaching from lysimeters, and the performance is similar to that in Classic, not exactly the same, but ag pasture, which these were lysimeters sown in pasture, has changed quite a lot since the Classic simulations were done. So I'm attributing the differences due to the change in the ag pasture model rather than anything to do with SWIM. And then from Sotirius in the USA, we've got some tile drainage and water table changes. And there the performance is similar to Classic. There are still some issues with not all the crops and cultivars being available in next gen as was in Classic and things like that. And Sotirius may like to say something when his simulations come up. This very busy slide covers the Hudson simulations. the primary data here is the storage of chloride down to various depths in the soil and the simulated soil water contents. The some of the graphs look a little bit naff, but when you look at the observed versus predicted, but I have included here a time series simulation on the far right. Sorry, the way my desk is set up, it's hard for me to do pointing. And that compares to, that's the same simulation as the middle graph on the left. So the Hudson 210 to 310 is the same as chloride 310. And so you can see that part of the really poor statistical validation in the observed predicted graph is due to the nature of the time series simulation and the variability in the observed over time. Is there anything that you'd like to add to this, Neil?
No, you've captured it. In the original SWIM paper, a lot of the analysis of that data set had to include the confidence interval of those dots, because chloride cannot be created or destroyed at those sorts of levels. So yeah, it's spatial variability in the field, not the model should not be replicating those dots.
Indeed, it would be odd if it did. The next graph, a set of validation data is from the lysimeters in New Zealand. On the left, we've got cumulative observed and predicted drainage, so pretty good simulation there. And on the right, there's leaching, and there's much more variation there, but it's not necessarily SWIM that's at fault. This is the time series version of that graph, and there are four replicates of each lysimeter, and I've included all of the data in the not just the mean in this simulation, and I'll try and see if I can get my mouse to point. Where's my mouse? There. So can you see my mouse? Nod, Dean, if you can see my mouse.
I can see it, Val.
Right, thank you. So for this blue line here that goes up here, the data points are there, 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 and there. So, and these are under highly controlled conditions. So given that, I'm happy with the simulation that we're getting out of this. The next set of data is from Satiri's work in the USA, and on the left we've got tile drainage by year with some error bars on it, and the lines are the simulated. As you can see, there's not really great matches there. In discussion with Satiri's, part of the issue is likely to be not having the right cultivars and things like that available yet. And there's also a regional water table, so that's outside the simulation, that's varying and will be causing some of the differences. I guess the good news is that it's capturing some of the ups and downs in the data, but obviously could be better. And there's also soil water content that's been collected from that same experiment, and it's doing a reasonable sort of job with a few exceptions, like not capturing some real spikes of very high water content. But unsure why from this particular experiment. And then there's another set of the same things. Satirius, is there anything that you'd like to add or comment to here?
Oh, no, Val, you covered everything about the US data set. Still, it's work in progress. We are working to get all the cultivars converted and some other functions we have put in.
Yeah. Great, thank you. For the sensibility, and this was actually the major focus of our work.
This is Fernando. I do have a small comment. I think the model it seems to be performing well. I think sometimes maybe if you compare the model with a regression fit, like a smooth regression to the data, you might see that it fits pretty well in some of those graphs. So like you were saying, you're not expected the model to capture a lot of the noise in the data.
Yeah.
So perhaps it might be useful, maybe not for this, but for something else or a paper to have a smooth regression and compare the model to the smooth regression. Because the rest of it is just noise.
Yeah, and that might be a good technique, particularly for that chloride from the Hudson trial. Yeah. Oh. So for the sensibility, Dean and I spent an awful lot of time checking lower boundary conditions, upper boundary conditions, and well, partly because that was necessary to get confidence in the model, but also these are some of the features that we've got in SWIM that are not available in salt water. So implemented are the potential gradient and seepage boundary conditions. We didn't implement no flow. For the surface boundary conditions, there's the same as classic in that there's curve number for runoff, but we've added in the possibility to get a combination of ponding and runoff, and implemented the power law runoff as well as an alternative to curve number. We've tested the response of simulated tile drainage to various tile drain parameters such as spacing, width of the diameter of the drains, depth to impermeable layer, and things like that, and they're all making sense. We've checked solute mass balance, and we had in a specific test because there was something really odd that was happening when we first started, where we could get a range of different water content values for the same value of psi, and this wasn't hysteresis, which isn't enabled in the model. It was simply that the algorithm for getting soil water content from psi was not operating as we really wanted it. In the tutorial section, we have simulations that show how to do things like create solutes, add solutes in irrigation water, how to, if you've got a plain Jane simulation, how to add in tile drainage, set different lower boundary conditions, and also how to check that there's mass balance in the water. And we can add to these as things go on. And finally, in the example simulation, we have essentially created a simple simulation and added in a memo which describes how to change a soil water simulation into a SWIM simulation, including information about how to set layering, boundary conditions, and things like that. And so, given all of that, how about we just click here and approve SWIM going to release?